I'm currently working at the Nanoforces Lab at the Universidad Autónoma de Madrid and the Condensed Matter Physics Center. I belong to this Nanoforces group. We are an experimental group with a long tradition in both low-dimensional materials and scan-improved microscopies. So already 20 years ago, during my PhD, I was studying the electronic properties of carbon nanotubes, and in particular, the influence of atomic scale defects on the electronic properties of these 1D materials. And during that time, we developed in our lab a very simple methodology to introduce single carbon vacancies in carbon nanotubes. Then, as Andres said, I moved to Germany and worked there on graphene oxide. There we realized that the material that we were producing was highly defective, and some of the studies that we did were also devoted to unravel the influence of these defects on physical properties of graphene. So when I came back to Madrid after some years in Germany, what I wanted to do was to perform systematic studies on the influence of defects on the mechanical properties of 2D materials. And this is what I will tell you about today. Okay, so in order to be more precise, I should change really the title of my talk and entitle it Mechanics of Defective 2D Materials. Okay, so I will talk basically about the effect of small atomic scale defects on the mechanical properties of graphene and molybdenum disulfide. Before going into our results, I want to make a very general overview of the mechanical properties of two-dimensional materials and also on the concepts that I will use later. Okay, so I will start by fracture properties. Graphene and molybdenum disulfide are among the strongest materials in nature. Okay, that means that they break at very high forces. So the breaking strength of a material is usually measured in one of these curves that we can you see my pointer? Oh, okay. Then in one of these stress strain curves in which we clamp a material by two sides, we pull, and at the point where the material fails, we will be measuring the breaking strength. Okay, so just for you to have an idea, graphene and molybdenum disulfide have a strength that is higher than that of steel and Kevlar that are usually said to be the strongest materials that we know. And it's usually said that a single graphene layer should be able to withstand the force exerted by the tip of a pencil with an elephant standing on it. Okay, so graphene and these materials are usually said to be the materials of superlatives. But there's one of them that is usually not mentioned, basically because it's seen as a weak spot, okay, in mechanical properties. We said that graphene and molybdenum disulfide has a very high strength, but at the same time, they are very brittle. That means that while it takes a lot of force to produce a fracture, once the fracture is produced, it propagates very, very easily. And the magnitude that characterizes this property is the fracture toughness. So here I have the fracture toughness of steel, some other metals alloys, glasses, and graphene and molybdenum disulfide. So you can see that the toughness of these materials is quite low. So in the mechanical fracture community, engineers, what they do is to plot this kind of graphs that we have here, in which one axis we have the strength of the material, and in the other one we have the fracture toughness. As you can see, graphene would be in the upper part of the plot, meaning that it has the high strength, but in the left part of our plot, meaning that it has the very low toughness. So what an engineer would desire is to have graphene here at the top right corner of our graph. Now, what happens if we focus on the elastic response? If we keep ourselves in the low force regime where the stress and strain of our material is linear, and the effects that we produce are completely reversible. So in this sense, graphene and molybdenum disulfide also have a very high in-plane elastic strain, okay? Higher than, similar to that of diamond and to that of stiffer metals, tungsten and steel. But the fact that molybdenum disulfide and graphene have such high strength and elastic modulus has nothing to do to the nature, really. Okay, basically these properties are related to the high crystallinity of the material, the well-ordered structure without the absence of defects, and the strong covalent bonds that form these materials that make them very resistive to external forces. But apart from this, they do exist some other properties that are highly related to the nature of these materials. So in the first studies of graphene and two-dimensional materials, these materials were treated as plates, okay? A plate in mechanical properties is just something that has a thickness that is much lower than its other dimensions. But if we make our plate thinner and thinner and thinner, then it turns out that our thin plate converts into a membrane. And membranes are very flexible objects. That means that they tend to ripple very, very easily. We can make an analogy to what happens with membranes, just looking at a piece of paper, okay? If we take a flat piece of paper and we elongate it, we will see that it requires a very high force to produce a small deformation. But if we wrinkle the piece of paper and try to deform it, we will see that at least in the first stages, it will require a much lower force to initiate this deformation, okay? Now, what will happen with the bending rigidity is completely the opposite. If we take a piece of paper, a flat piece of paper, and hold it just by one side, we will see how it bends easily. But if we now create some static wrinkling and hold it by one side, we will see that it stands alone quite easily. So this is an analogy to what happens with membranes, okay? The elastic response, the elastic constants of membranes depend very much on their corrugation, and the bending rigidity also depends very much on their corrugation. Indeed, there was a full theory, mechanical theory developed during the 70s and 80s in order to understand what was going on with biological tissues, mainly lipid bilayers. And from this theory, very complex theory, we can extract two very simple sentences, let's say. First of all, the fingerprint of a membrane behavior is that membranes have a negative thermal expansion coefficient. That means that when we heat up the membrane, in order to accomplish new and higher amplitude fluctuations, this membrane will shrink in plane. So if we look from upside, we will see that the area of the membrane is reduced when we heat it up, okay? And this is usually said to be a negative thermal expansion coefficient. The other thing that we also saw from a very intuitive point of view is that the elastic coefficient, the elastic constant of membranes, highly depend, are not a constant anymore as in a plate, but they highly depend on the fluctuations of wavelength. Depending on the wavelength of the corrugation that we have on a membrane, we will have different elastic constants. And this, and in particular, the in-plane elastic modulus depends on the wavelength with the power law, like the one we have here in the screen. Okay, so talking about extreme properties of 2D materials, I cannot forget about friction. Both graphene and molybdenum disulfide are amongst the best lubricants that we know. Okay, they have very low friction coefficient with other materials and between 2D materials. And this is basically due to the convergence of several facts. First of all, they're quite inert, they're chemically stable, so their adhesion forces to other materials are very low. The contact area between 2D materials and other materials is usually quite low because they're very, very smooth. And then on friction, on the tribological properties and behavior of these materials, we also find some exotic properties that depend, that are related again to their very low bending rigidity. For example, friction in two-dimensional materials are layer dependent. The higher the number of layers you have, the lower the friction that you will have. And that's basically because friction in very thin, these very thin materials, it seems to be dominated by a puckering effect. They're so bendable that whenever you approach the tip to these materials, the material tends to pucker up from the surface and adhere to whatever you approach. Okay, so I hope somehow I convinced you that 2D materials are a kind of interesting cocktail regarding their elastic and in general mechanical response. And although we know quite a lot about them, there are still many questions to be answered. Okay, one of the biggest questions on these materials is whether continuum mechanics can or not the effects that we will observe on these nanostructures. Whether plate theory or elastic or membrane theory will be better describing these particular objects, how to deal with the presence or absence of a substrate, what are the intrinsic values of the elastic constants of these materials, if there are, and how to deal with the impact, of course, as I told you, of defects and wrinkles. So many open, interesting questions to address, but unfortunately, the experiments on these materials are usually difficult to perform. Okay, when we think in making mechanical studies, it seems quite simple. You clamp your piece of material by two sides, and then you pull and measure the deformation strain and the force that you apply. This is very simple to say and to think, but very difficult to do if we are dealing with something that is one atom thick. Okay, so there are some devices that have been developed in order to be able to pull a single graphene sheet, but they're very, very challenging to build. And once they're working, they're quite unstable. This issue has been overcome many times by depositing graphene on flexible substrates, deforming the substrate, and measuring what happens to graphene. But usually here the problem is that measuring the strain that is transferred from the substrate to the graphene or other 2D material, it's difficult to estimate. Now, there are two other ways to overcome this issue, which are quite similar. One of them is to prepare graphene blisters. Okay, so we deposit our 2D material on a substrate that has like circular holes on it. And then we apply a pressure difference and measure like a classical blister test. And the other one, and the one that I will use and I will be talking about, is to, again, prepare this kind of graphene drumheads in which we have a circular portion of graphene suspended on a, on a hole. And then we come with the tip of the AFM and push on the center of this drumhead, graphene drumhead, or molybdenum disulfide drumhead. So before I go into the results, let me remind you the motivation of this work. Okay, when we started these studies, there were already reports in the literature on the intrinsic properties of graphene, pristine graphene, the one that we obtain from mechanical exfoliation, okay, and that we usually use in the lab. And there were some other studies on the mechanical properties of graphene obtained by chemical methods, which is usually full of defects. It has a very high density of defects, but there was nothing in between. So it was our aim to fill this gap here, okay, and try to perform systematic studies of the mechanical properties of 2D materials as a function of the density of defects. And for that, we will use this technique that we developed already some years ago in order to induce single vacancies in these materials. So what we do is we use argon ions at a very low energy that we use ions with low energy in order to irradiate our materials. So in each of these events, we remove just one carbon atom or molybdenum or sulfide atom. So in this way, we can induce a very controlled density and type of defects. For the case of graphene, we were able to image these single vacancies by scanning tunneling microscopy. And we also perform Raman spectra and to correlate well-established relation between the Raman peaks and the density and type of defects that we had in our samples. For the case of molybdenum disulfide, we use the same technique. We irradiate it with argon ions in order to get single vacancies, double sulfur vacancies, and molybdenum vacancies. But we also irradiated in a field ion beam with gallium ions in order to get multi-atomic vacancies, okay, larger vacancies. This time with molybdenum disulfide, there were no well-established relations between the Raman spectra and the type and density of defects, but we could establish these relations in our work, as you can see here. Okay, we have, as you can see here, I forgot to say, we have TEM, transmission electron microscopy images of the irradiated samples. So we can determine both the type of defects that we have and the density of defects that we have in our samples. Now, the technique that we will use in order to characterize these materials, I told you a bit already. We have a sample that has predefined holes on it, and we deposit our 2D materials on top. So this is an atomic force microscopy image of one of our drumheads. It is important to say that we select drumheads that do not present folds, wrinkles, and so on. So we don't use any drumheads that we obtain. We just use the ones that seems very flat and they lack of slack. Now we come with the tip of an AFM using a diamond tip in order not to break it, okay? So in some of our experiments, we reach the fracture of the material. Then we will be able to measure the fracture properties, basically the strength of the materials. And in some of our experiments, we will keep our indentations in the low force regime. And in this regime, we can determine both the elastic modulus of the material and the tension of our layer. So the experiments that we perform are usually as follows. We select one of these drumheads. We perform indentation experiments. Then we irradiate the sample with a certain amount of argon ions. We check by Raman spectroscopy the density and kind of defects. And we come back to the same drumhead in order to keep on measuring, okay, the elastic properties as a function of defect density. So we always track the same drumhead after each irradiation dose. Okay, so let's start with the fracture properties of graphene. This is the strength that we measure for graphene as a function of the defect density that we induce with this argon ion technique. As you can see, the strength, what we observe is that the strength is reduced to 30% of its initial value already with very, very low defect density. Okay, so at this point, the percentage of defects that we have in our sample, it's around 0.3%, so very, very low. That means that the distance between defects, it's around 7 nanometers. Okay, so remember, we are dealing with single carbon vacancies. This is quite interesting. And we got quite happy when we saw with these results. And they support some previous simulations that were in literature on the tendency of the strength with material defect density. Okay, what happens with molybdenum disulfide? In molybdenum disulfide, we have a very similar behavior. If we deal with mono vacancies, we see how the strength is highly reduced by the presence of these vacancies. And here we can go one step forward also, because we were able to create vacancies of several sizes. Okay, so if we go to large vacancies, to multi-atomic vacancies of between 1 and 2 nanometers in size, we see that the strength is much more reduced, okay, for the same or even smaller defect density, vacancy density. Okay, but one interesting thing is to compare, let me see if I can move this, yeah. The strength of our materials and how it is reduced with the strength of the materials that we usually consider very strong materials, okay? So while the strength of graphene is highly reduced, and the strength of molybdenum disulfide also, the strength of this defective material is still higher than that of steel and Kevlar, okay? Now, a very interesting thing is what happens once we create one of these fractures. So in order to study that, what we did was to perform scanning electron microscopy images of our drumheads. This is one of these images. This white halo that you see here is the border of our drumhead. And the thing that you see here are the folds of the broken graphene layer, okay? So the same here for molybdenum disulfide. You have a broken membrane that it's folded at the edges of our drumhead. Now, this is what happens if we deal with pristine material. Now, cracks, fractures propagate very, very easily. We have a huge tear length. So once we produce a fracture, a small fracture, it propagates in a catastrophic manner. And this is for sure nothing that an engineering would want if you want to build a device out of graphene or any other 2D material. Now, what happens when you have defects. When we have defects, things become a bit better. So this is an SEM image of a pristine drumhead. This is an SEM image of a drumhead in which we introduce very, very low density of defects. And the following one, this one, is when we introduce even more defects. Okay, so measuring here, we can plot the tier length, the length of our tiers, as a function of defect density, and see how defects are able to reduce in more than 2 orders of magnitudes the tiers created in graphene. A very similar thing happens with molybdenum disulfide. As we induce defects and keep inducing, the tier lengths are strongly reducing this material. This is not surprising, not very surprising, or not typical of the 2D nature. Okay, this crack deflection and bifurcation brings out higher energy to overcome for the crack to propagate. And this is indeed, I mean, defect creation is indeed something that is used in fracture mechanics in order to increase toughness in macro materials, in 3D materials. Now, we saw 2 different effects. First, defects decrease the strength of the material, but at the same time, they also decrease the crack length, which is a very good news. And at the end of the day, what the magnitude that is able to describe these 2 things at the same time is fracture toughness. Okay, and if we plot the fracture toughness of graphene and molybdenum disulfide with the presence of this very small amount of defects, we see that fracture toughness increases. Okay, good news for engineers. So that basically means that when introducing these amounts of defects, we are moving graphene from this part of our plot to a bit lower in strength, but much higher in toughness. So it will be convenient for their use in devices. Now, okay, let's change topic now completely. Let's focus on the elastic part of these materials as a function of defect density. What happens with the elastic modulus of a material if you introduce vacancies, atomic vacancies in this material? So when we started these experiments, what we were expecting, and also some molecular dynamic simulations were predicting, is that if we start by graphing and we create single vacancies, the elastic response of the material will be decreased. So we will be softening the material. The elastic modulus should decrease with the presence of vacancies. And this is what we were expecting. But when we started making these experiments, we found out that instead of finding a decrease of the elastic modulus as we were expecting, we found up a very, very deep increase and a steep increase of the elastic modulus for very low defect densities. That at higher defect densities turns to start decreasing. Okay, so this is something that we were expecting, but this initial increase in the elastic modulus of graphene with the presence of defect was something that we didn't expect at all. And okay, so and as you can see, the magnitude is not low. It's now at 10%. Okay, the elastic modulus doubles. Okay, for these defect densities. So this stiffening mechanism took us a while, let me say, to unravel. We talked with many colleagues, but finally Paco Guinea and Misha Cannoso came up with the idea that in order to understand our results, we cannot forget that graphene is not flat. It's never flat, but it's always wrinkle or ripple, okay? It's a fluctuating membrane. So it will have corrugation, independently if this corrugation is dynamic or static. So our results can be understood in the framework of this elastic theory of membranes, if we take into account that graphene behaves as a membrane. Previous experiments had shown by that time that graphene has a negative thermal expansion coefficient. It shrinks when you heat it up. And that was the fingerprint of the behavior of graphene as a membrane. But there were now other experiments showing dependence of the elastic constant on the wavelength of the fluctuations of graphene. And this is indeed what we think we are observing in our results. So the main idea to justify this initial increase in graphene elastic modulus is that defects are somehow able to quench, to reduce the corrugation of graphene that has a wavelength higher than the distance between these defects. And with this idea in mind, and with this predicted behavior of the elastic constants of membranes as a function of the, of the wavelength of the fluctuations in our membrane, we can quite well fit our experimental results. Okay. Then the softening part was already described in the literature, and it also fitted our results. Okay. Now, this was quite novel. Okay, and that meant that graphene does indeed behave as a membrane. So we started thinking in what consequence should this hypothesis have. So first of all, if defects are able to suppress thermal fluctuations, they should also influence this thermal expansion coefficient of graphene. And then if we are able to suppress somehow corrugation of graphene by any other way, we should also see this stiffening of graphene. And one way to suppress corrugation of a membrane is to apply global stress. Okay, so in the next slides, I will show you our efforts in trying to address these two questions. Okay, so first of all, let's focus on the thermal expansion coefficient of graphene as a function of defect densities. I won't go into the details. Let me just tell you with a very simple manner, just by heating up our samples and measuring the tension of these graphene membranes, we were able to estimate the thermal expansion coefficient of graphene. For pristine graphene, we got a quite clean tennis graph of the tension of the membranes as a function of the temperature that allowed us to estimate the thermal expansion coefficient. That turns out to be very similar to that obtained by other results, by other experimental techniques. So we went on and studied our samples once we induced the effects. And we see how the thermal expansion coefficient of graphene, okay, approaches to zero. It goes from a negative value to a value closer to zero when we induce defects in our membrane. So this is a very strong indication that defects are somehow able to decrease thermal fluctuations. Now, this time, we were able to convince theoretical colleagues in order to make dynamical simulations, molecular dynamic simulations, okay? And what you see, and they were very, very elucidating. What you see here are plots of the amplitude of thermal oscillations for two temperatures, both for pristine graphene, the upper ones, and for graphene in the presence of defects. The similar defect density and defect type that we have, okay, carbon symbol vacancies. And if you check here, the amplitude of the oscillations, not in the defects, but in the rest of the membrane, is lower than here. So thermal fluctuations are highly reduced when defects are present. How to understand that comes if we now plot the strain maps of our samples. So what happens is that these single vacancies are able to produce in their surroundings very local stresses that are able to suppress oscillations. So this is a very intuitive picture for me. This is a pristine graphene layer, and this is a layer with defects, okay? As you can see here, while the defect by itself, the two atoms nearby the vacancy oscillates, the rest of them keeps much more quiet, let's say, than for the pristine case. So now we know a bit how strain and vacancies are related, okay? Vacancies create very local strains, but high strains, although local, that are able to suppress corrugation in graphene. Very similar to what we had in our wrinkled piece of paper. Now, the other way of reducing corrugation of a membrane is introducing a global strain, not a very local strain. And in order to do that, what we did was to use something similar to this blister test that I was showing you just at the beginning of the talk. So what we did was to prepare graphene drumheads as the one we were using, but now we induce a pressure difference between the outer part and the inner part. Okay, we have a higher pressure in the outer part, and now our atomic force microscope is embedded on a high pressure chamber. Graphene, it is very, very impermeable, so that means that even very small molecules will not pass through our graphene membrane. And now when we are at this point where our membrane is deflected, okay, and it is a global strain, we can perform our indentation experiments and measure the elastic modulus of the material. So this is the elastic modulus of the material that we obtain as a function of the strain that we induce by these pressure differences. And we see how for very low pressure differences, the strain is the one that we measure, we expected. And as we introduce global strain by inducing a pressure difference, we keep on obtaining a higher and higher elastic modulus for our indentations experiments. So let me summarize on the elasticity of graphene. Okay, we saw that contrary to what we were expecting, we observed an initial increase of the elastic modulus of graphene when we induce single carbon vacancies on it. Focusing on this initial increase, we made also an experiment trying to study the thermal expansion coefficient of graphene as a function of defect density, okay? As you can see here, I have this on these two axes, and we can see that the thermal expansion coefficient of graphene reaches 0 at the point where the elastic modulus of graphene tends to saturate. So it's not only the effect, but also the numbers that agree. And then we tried to reduce rippling of graphene by other technique, by inducing a global strain, by inducing pressure difference. on graphene blisters. And there we observe again that the elastic modulus increases and then tends to saturate as we induce the global strain in our membrane. Okay. Again, not only the effect, but also the numbers agree. Okay. And the maximum elastic modulus that we measure in the case of defects, it's very similar to that we find when we induce a strain in our membrane. So with this, I'm already finishing. Let me just give you 2 minutes, talk about 2 minutes about friction. Okay. Now I will change topic completely, and I'll tell you about our latest work, which is related to friction. Okay. And again, we were interested in studying the effect of very small defects on the tribologic properties of graphene. As I told you, graphene is one of the most or the better lubricants that we know. Now, what we did this time, we are improving a lot our technique in order to produce defects. And what we have learned now is to induce a gradient of defect density in one single sample. Okay, so in this sample, we will have very high defect density in this size and very low defect density in this size. Okay, so this is a friction force map of a sample that has no defects here and a quite high defect density at this point. This is very convenient with friction because friction is highly dependent on the contact area of the two bodies that you have. But with this technique, we can study the dependence on defect density on just one scanning line of our atomic force microscope. Okay, so we see very clearly how friction increases, okay, with the increasing defect density, which is nothing new. But what turns out to be quite interesting that if we zoom in into these areas, we are able to count the defects that we have. So friction images allow visualizing really, really well single carbon vacancies, which is something that we didn't know before. Now we have been able to image these single carbon vacancies also by looking at stick slip atomic events. But when coming to the macro studies, or let's say micro studies, if we plot how the friction coefficient varies with the density of carbon vacancies, we see how it increases, okay, with the, here we have the mean defect distance, okay, but it increases as we approach the defects. But as if we compare, sorry, our results to other studies in the literature where they perform different modifications in graphene as fluorination, oxidation, or hydrogenation, we see that single carbon vacancies are much more efficient, increasing friction than this other modification. And that, sorry, seems to be related, okay, with the fact that when we produce one of these vacancies and perform a friction map, we see a very increased and localized friction increase on top of the vacancy. But then we observe also that the surroundings of the vacancies are also highly affected by the presence of this missing atom. Indeed, this contribution, which is not really on top of the vacancy, is 70% of the increase in friction. Now, if we overlap the strain maps that we obtain in molecular dynamic simulations of a single vacancy of carbon and our friction maps, the area that is affected is quite similar. So that tells us that, again, this property of graphene, that the elastic response is highly modulated by local strain created by vacancies, is this time also governing friction properties of graphene. Okay, so with this, I think I will stop. I made my time. Let me just make a brief summary. We saw that introducing defects in graphene and molybdenum disulfide is not always as bad as we would think initially, okay, because they increase the toughness, the fracture toughness of both graphene and molybdenum disulfide. We see quite exotic observations on the elastic properties of graphene, and we could relate them to the presence of corrugation. And we saw that also this corrugation is higher, influencing and governing the friction properties of graphene. And before I finish, let me tell you that I have to acknowledge all the people that made this work, not collaborated, but made this work. Guillermo López Farín, which is the responsible of most of the elastic measurements of graphene. Aitor Zambudio, that made all the friction related studies. Yolanda Manzanares, that was the one in charge of this crack propagation studies. That from the experimental part, we also had a lot of more support, but also in the theoretical part, we have very, very close and good collaboration. So thank you all for your incomes, and of course, thank you for your attention.